Welcome back to our book club for spatial computations in R. As you can see, we're going to take on chapter 7, which is an introduction to the SF and stars packages. And I just thought it'd be neat to see that a couple of the examples that we'll encounter are look at the counties of North Carolina and also the city of Olinda on the coast of Brazil. Some packages that we'll encounter today along the way. The SF package stands for simple features. This has been a larger effort by folks in the geospatial R community, including the authors of this textbook. This replaces some of the older packages, SP, RGOs, and RGoodle. Some of the motivations include that SF has good interface with the tidyverse ideas, mentality, naming conventions, compatibility, etc. Wanted users to be able to do geometrical operations in both geos and S2 geometry, the notions of coordinates, projections, and also for ease of coordinate transformations. SF objects have a data frame or tibble, as you would see elsewhere in the R programming language. But in particular, the SF objects has a column, we're going to call that SFSC, special simple features column, where the geometry is. Where the geometry could be the point, the line string, the polygon, etc. So when we have the metadata of an SF object, we have that SF column, the geometry column. Anything else in the data frame would also be described by an attribute geometry relationship, AGR. I like how this textbook gives us this visual example of if we have output or a description of an SF object, how we could view that. So we can see in red, we have the number of rows and variables. For the shapefile or the feature, here in orange, we have the metadata, which could include the geometry type, the dimensions, the bounding box, and the projection coordinate reference system. And then below in green, we have the data frame, the information that's stored in the simple feature. And then finally, in the bottom right box, kind of a brownish color. This box here, we have that SFC, the geometry column. In particular, SF objects have that geometry column, even if we do operations such as intersections or cropping, that geometry column will always be there unless the programmer explicitly removes it. So we'll look at an example. The folks who made the SF package has this geo package available to us as an example data set that talks about North Carolina, a state in the United States. This is a multi-polygon dotted in X's and Y's, bounding box, and has the North American CRS, a North American CRS. Thank you. North American data. Overall, in this chapter, we are seeing what capabilities we have with the SF and STARS packages. There are a lot of different functions to mention or cover. The textbook mentioned some of them. Here in the book club, I'll mention a slightly smaller subset of those as well. One skill to consider immediately is when you have an SF object, which is for the most part a data frame, we have a lot of similar skills, such as subsetting. So for example, we could take the North Carolina data frame, and if we subset like this, numbers, column, numbers, this example will grab the records 2 through 5, or rows 2 through 5, and the variables 3 to 7, or columns 3 through 7, as you would find elsewhere in the R programming language. Visually, we could think of a subset as we're going from a list of counties in North Carolina down to a smaller list of counties, a subset, of course. Throughout, when I grab the code and information and put them in our book club notes, for the image code that the authors provided, I have them in the folding code box. So in this example, in addition to having a couple of these subsets in the picture above, the text was made by finding the centroids and then using that for the labels. As I was mentioning before, every SF object has that geometry column. There is a drop argument when working with that. By default, it's false, meaning that the geometry column is always selected, even if you do more operations like this. If for some reason you want to drop that geometry column, maybe for memory reasons, you could set this to true, but at that point, you're only grabbing the data about the situation and you're dropping the spatial aspect. So that should be only done in very intentional cases. Otherwise, leave the default drop being false to stay in a situation where you can talk about the geometry. Internally, selection was the spatial object, whether it's SF, FSC, or SFG, is done in a way that we think about spatially intersecting with that object. So that caution is done with the function st intersects. For example, if we have the pictures at the top of the screen, we could ask about the intersections thereof. NC5 had 5 objects in it, and it'll ask amongst the 7 objects of NC7 where there were intersections. So again, NC5 has 5 polygons, and then ask which of the NC7 polygons were the intersections of the original 5. Usually, especially in larger data sets, this is there are not all that many intersections So you would want to store this in your computer in a sparse way to save on memory and computation time. But for now, because we do have a relatively small data set, we could look at the whole entire matrix if we wanted to. Once again, NC5 had 5 polygons, and we're asking amongst which of those NC7 polygons were their intersections. So we have a true, false, Boolean, or predicate. This object labeled I here at the top of the screen, this is given a class in addition to a list, or sometimes we think of this as matrices in R. We have this class here, which stands for sparse geometrical binary predicate. That is, when you have operations such as intersections, what's going on internally is operations like this, but being compatible with the other geometrical objects that we might encounter in SF. With this and other classes, you could look up the methods available to you. When we have a situation like this, but actually the sparse representation, we could look at it as a data frame, as a matrix, and there are other operations that you could do as well, just in case you're curious. Over the past nearly 10 years in the R programming community, the tidyverse has been a modernization. The SF package, you could read and write objects with the read and write SF functions, as you may expect. Some things to consider at that point is that you would have a tibble, not just a data frame, that is. Especially with larger data sets, you would not want to print any output at that moment when reading or writing. And be careful, because this may overwrite existing data by default. Now, of course, we're not going to talk about the entire tidyverse, but want to quickly mention that for those that are familiar, which is probably this audience here, the usual dplyr, ggplot, and tidyr capabilities are still available or still desirable. But if you're trying out tidyverse functions on the simple features or spatial data, you might want to just be aware of some of the things that happen. For example, we could still, as you can see on the right side of the screen, we could still use the summarize filter and distinct commands. It's just that with the overloading, the commands do a couple more things with the SF objects. So for example, when you run summarize on SF objects, there are internally 2 special objects. They're optional in that they have defaults. The do union will determine whether group geometries are union on return. And we talked about in the past, the reason why we want that is that if they are a union, then they form a valid geometry. We could also ask if the data forms what's called a coverage. If the geometries form a coverage, that is, they do not have overlaps. Especially for some of the more complicated data sets we're going to encounter pretty quickly, it's useful to leave the default as false. But if you do know that your data is clean, that it is a coverage, that there is no overlaps, then you could set that to true to help you speed up your computational time. For the filter command, this works as well. If we take our list of counties in North Carolina, we could filter for any of the data frame columns. Here, we're going to grab the information where you have Orange County. And for a neat computation that's found in SF, you could form a buffer of 50 kilometers. And then you could also, in a different workflow, take those North Carolina counties and filter where, once you have that buffer, where that buffer is true. So where we are within 50 kilometers. Putting that together, we get this map here. Orange County highlighted in orange. And we are also highlighting in the black double line which counties have areas that are within 50 kilometers of Orange County. Which, if you pause and think of that mathematically, it's actually a difficult calculation. But fortunately, the folks who make these packages help us do these computations in just a few lines of code. Quick note, the distinct message selects distinct records, but internally, the logic is done using the st equals function along the way to evaluate the distinctness of the geometries. That is, because you are dealing with spatial data, you have to worry about overlapping areas. Okay, looking now at spatial joins. For joins, the concept of left, right, inner, or full joins remain for data sets. Thinking back on data sets you might have merged before. The issue is that when using spatial joins, each record, each row of observation may have several matched records. So there is a big complexity there. And one way to deal with that is to select the largest overlap. Let me perhaps zoom out a bit. So on the top picture, the gray lines in the background are the counties. And a very much more colorful rectangle is a grid that has been made. The grid labeled A1 through G10. What we're doing, as you can see in the bottom picture, is taking the counties and labeling them with whichever grid label they overlap with the most. So which one do you want to focus on here? So we have this county here in the top, where you could see that it has some overlap with grid cells B2, C2, C3, D2, and maybe D3. The way the calculations are done for the join is because this county overlaps overlaps with C2 the most, that is, this overlapping region is biggest in the C2 cell compared to the other cells available, that county, like you pointed out, is labeled C2. There are other ways to handle the join. You would need to turn off this parameter, but then probably have to worry more about the internal mathematics. An SF object can be created from scratch. Here we have intended XY coordinates, casted those as point objects, which is set point command. We could take that list of points, because we want a geometry column in the SF object, we could set the simple features coordinates. But in order to do that, be sure to tell the system which projection you're working with. So then that all gets collected into one column called SFC. On top of that, you can make a data frame here with two columns called elevation and marker. And then what we have at the bottom of the page is everything put together. We have the elevation column, the marker column, and the geometry column. So you can see we have three observations, two variables. Note that the variables are counting for the data frame or tibble. The two fields in this count, the two fields does not include the geometry column. So that might come up from time to time. When creating SF objects from scratch, some functions that the authors mentioned along the way are sample. You could induce some randomization into your processes if you're doing, say, simulations. You could make grid, which you saw up here, make a grid. And you could do interpolations. So that's all available to ease your computational processes. Yes, thank you for the chat message. At the moment, I tried to upload this to our GitHub page, but for some reason the GitHub push did not work at the moment. Hopefully someone will figure that out. One of the motivations for the SF package was to handle the ellipsoidal coordinates. So we have a point object represented by the red dot. On the image on the left, we could see that the red dot is within the quote unquote rectangle. And on the image on the right, the red dot might not be inside the rectangle. The more modern approaches is expressed by the image on the left by the S2 geometry. Older approaches are done by GEOS, the system mentioned on the right. So by default, SF uses geometrical operations from the S2 geometry library interlaced through S2 that will handle the ellipsoidal coordinates. And as in the image there in the top left, if we have that polygon and that point, we would see that the intersection reports as true, that point is inside the polygon. If for some reason you want to not use S2 geometry and want to go back to GEOS, you could tell your whole workflow, your environment to turn off S2 with this command here. And what happens is that the intersects would then assume planar versions of longitude and latitude, and the intersection would report an empty or nothing in the intersection. Now, this particular command might affect your entire workflow. So at least I know for my purposes, I did not run this chunk of code just to be safe. Okay, so we were about halfway through. As you could see, that was the introduction to the SF package. Do folks in the audience have additional comments or questions? Okay, so we'll go ahead and move on to the stars package. For the most part, for those who practice with geographical information systems quite often, you probably think of your data as raster layers, and that could generally be handled these days with the Terra package for dealing with rasters. To motivate or why we might want to also think about the stars package, this allows for dynamic or time variant raster stacks. This aims at being scalable, especially for very big data that might be beyond what most folks have on their laptop computer. A strong integration with useful functions from the Google library. When you think about rasters, by default, you might have regular grids, but in particular situations, you might have rotated, shared, rectilinear, or curvilinear rasters. So if you have that perhaps unusual situation, perhaps the stars package could handle it better. The folks who work on these packages know each other quite well, so they make sure to ensure integration with SF, follow the tidyverse principles. But as the textbook arrangement is concerned, you probably figured that the motivation at this point is to handle arrays or vector or data cubes. the folks in this book club presented data cubes in a previous session. In my naive knowledge, data cubes includes multiple rasters put together, but you also might have a reason for the extra dimension, such as talk about time or other variables. The folks who made the stars package provide this data set for us that refers to the city of Olinda in Brazil. We're going to look at the internal metadata fairly often. Here we have a stars object with 3 dimensions and 1 attribute. Now, the 3 dimensions are X, Y, and the band. Now, the band we might have discussed in the past is when you're looking at satellite data, it actually takes pictures in multiple ways, such as red, green, blue, near infrared, ultraviolet, and other ways of imaging. So we could see that in this data set, we're looking at satellite imagery of this city, but in 6 different points of view. Those are the bands 1 through 6. So we have these 3 dimensions of the data. The 1 attribute is labeled here, this numerical variable, which is given a summary command. Now, for various mapping purposes, mostly to get the coordinate system correct and aligned in other calculations, there are these aspects here. Whoops, I should have used a different word that the textbook will tell you more in particular if you're interested. So with that, we're looking at raster data. So as you may see in other GIS textbooks, we could look at a human vision visual of the raster data. On the left, we have our red, green, blue view of the satellite data. And on the right, we have what's called a false color point of view with near infrared, red, and green. The false color point of view leads us to a discussion usually used in the agricultural communities where you want to see where there are plants and trees, etc. Maybe mention that again later. Like what we did with the SF package, where we want to mention some of the capabilities as far as programming is concerned. For subsetting, we could use the square brackets as usual. In this example, that's grabbing attributes 1 and 2, index 101 through 200 for dimension 1, and index 5 through 10 for dimension 3. Being very careful here that we do have a couple commas, and what that did was actually omit dimension 2 in the subsetting. So to say that another way, when we have the stars object, we're grabbing the attributes first and then going through the dimensions. You could also use other functions along the way to help you with your filtering, such as the sequence function from base R. Now, in this command, when you run this through the dimension function, you'll get your XY data along with your band. And similar to the SF default of keeping your metadata or your additional column about the information, this will stick around even if you don't explicitly ask for it, this comma here, really. But if for some reason you want to drop that extra information, that ability is there for you, but caution, just be very intentional about that. When you bring in dplyr, you could use its filter command as well. Let me double check something. Here we are looking at certain longitudes, and that will change where we are along the x-axis. You could also use the slice command in dplyr. That will, let me see if I could keep this on one page. Here we're looking at band 3, which I believe is the blue colors in the satellite data. So instead of having all 6 bands, you'll notice in the bottom information that the band is gone. The previous object at the top had 3 dimensions, namely X, Y, and band. But if we select only band 3, now we're down to 2 dimensions. Another ability that we have in these operations, aided by the stars package, is cropping. We could set a buffer around the stars object labeled R, a buffer of 500 meters, and we have the image below, which will still contain a lot of the metadata, tell you how the XY extents are going. And we have a picture of the new raster here, highlighted with the brown circle. And as a convenience, you don't necessarily have to type out all this code. There is a wrapper function called crop that will do that as well. Yes, indeed, the largest overlap. There's more advanced discussion about redimensioning. Admittedly, I did not type out everything or completely understand everything, but just to mention it real quick, the authors note that they made some functions for convenience in case you're doing more advanced manipulations of the data cubes. The aperm function will transpose an array by permuting the order of the dimensions. So if you wanted some of these dimensions in a different order, you could reorder them. Attributes and dimensions could be swapped. So this is like, to me, kind of an analogy to pivot wider and pivot longer. And those are done with here in the stars objects with the split and merge commands. So compared to before, if we split the object, now we have only 2 dimensions, but with 6 attributes. because these attributes are talking about the bands, really, the band data. But still with the XY coordinates. The inverse, it would be take the merge of the split object, put everything back together in bands, and then restore how that information was called L7 ETMs. Multiple stars objects, as long as they have the same dimensions, can be combined using the classic C command for concatenation. Extractions can take place with the st extract command. So say if we have that stars object for the city of Olinda, Brazil, we focus on the SFC, the simple features geometry column, and grab 20 of those locations. We could save the data with that random sample of 20 points. So now our geometry are 20 points. But still with the satellite data among the bands. What that's doing is that we have 20 points randomly sampled in our bounding box. So we could see that the ones in yellow correspond to places on land, and the ones in red correspond to places in water, namely the Atlantic Ocean. And you could do some machine learning. Here, a quick example using linear discriminant analysis, the powerful function coming from the mass library. Long story short, at least for this particular seed that the authors recommended, the predictions seem to be doing pretty well in predicting what is land and what is water. For the sake of the video and scheduling, I think I'm just going to read off the rest of the materials fairly quickly. So bear with me. For computations, these are rasters. So there are various things you can do, such as take a logarithmic transformation. You could apply mask, and you could actually turn mask off as well. We were doing some sampling. As the folks mentioned in the previous chapters, we could do some aggregation. Before we had 3 dimensions in one attribute. If we take the average of the bands, of the 6 bands, we're down to x's and y's, and we have now the one attribute for the average. More practical situation is to calculate the NDVI, normalized difference vegetation index. Once again, that helps us see where there's plant life in satellite imagery. We have the function that computes this metric using the near infrared and the red bands. And we have the NDVI now computed as the attribute. I don't think the authors did an example here, but this is good information for the future. Aggregation of over a temporal dimension that is over time. As anywhere else that you're working with time series in computer programming, it might be surprisingly difficult. But fortunately, there are helper functions along the way, and you could deal with timestamps, whether you have the started time intervals. You could literally affect the make intervals parameter, or there are simpler ways to describe that if it works in your situation where you could just state the time interval. So for example, we could look at a case study of air quality. This is in Europe. This is with a data cube. For our GitHub repository, I copied the data as they had it in their GitHub repository. I was curious about this naming convention. DE stands for Deutschland, aka Germany. And NUTS is this statistical regions of Germany. In the United States, we go from country, state, county, city, zip code, census tract, with maybe some overlaps. What NUTS is their German version of this. Länder, Riesa, etc. So with this data cube, we have space-time dimensions, 70 objects in space, many locations in time. Visualizing the information for now, we have this data here, time on the horizontal, the information recording stations on the vertical. A lot of information, but we also note that it's for practical reasons, maybe missing sometimes, wasn't recorded all the time, and information may be sparse in nature. The attribute we're looking at, PM10, that's particulate matter of relatively large compounds in the air. This affects how people might have difficulty breathing. And we're looking at the 70 locations in the country of Germany. The colors are by that metric, PM10, the particulate matter. And this is summarized in this case using the aggregate command. So the vector cube aggregated by mean. We could also, for example, take our object, filter it in the time dimension, and produce some nice plots like this. We could see that the days of January 3rd, 4th, and 5th have a lot more yellow, meaning that there was a lot more air pollution on those days. Or we could visualize our time series like usual. With the time series, folks who work with time series might like using the XTS package to help with the calculations. art of programming. For another example, the textbook authors of this textbook and the geocomputational textbook like this example coming from the city of Bristol in England. When we think about transportation, how people usually get to work. So we have these origin destination data zones in the greater Vince area of Bristol. And we're asking if people or how many people go from one zone to another and how they do that, whether it's by car, by train, by bus, etc. We have multiple zones, and zone 33 is highlighted in this image. So when you bring in the data set, we have the origin, we have the destination zone, we have the number of trips by bicycle, by foot, by car, where there was a driver, and by train. Skipping over some of the pre-processing, they made an array, and they made sure that the array clearly defined the origins and destinations, but made sure that the order of the zones, like zone 1, zone 2, zone 3, matched with the original data, just in case. So with the stars object, we could do things like apply a log transformation because some of the numbers were much bigger than others. That is, some zones had many more people than others. You can see in the bottom left with the yellow that most of the trips were done by car. And when we go over the information using an apply command, we could quickly figure out which zone had the largest numbers of travelers, and that's why the textbook authors focus on zone 33. There are other examples of using apply to grab other ways to talk about the data, such as origin totals, destination totals. But here we could see the origin destination plot. It's a little hard to see, but the overall idea is that most people are going from the outside going into the center of the city. Now, there may be quick concerns about, well, some of these zones are bigger than others. Wouldn't that affect the calculations? So you could normalize in various ways. One way you could do this is to divide each zone by its area. And then you could plot it this way, which once again emphasizes how most people are driving to the city center. And then finally, towards the end of the chapter, I did not transcribe everything, but suffice to say, if you have a geo package, there are ways you could take these data sets with the attributes and dimensions and turn them into rasters with help of the SF package. And that's the end of my presentation.